Is dark matter close to us or far away? How dangerous were those recent solar storms? And is there any way we can make the Drake equation better? All this and more in this week's Question Show. Welcome to the Question Show. Your questions, my answers. As always, wherever you are across my channel, if a question pops into your brain, just write it down. I'll gather them up and I will answer them here. All right, let's get into the questions. Ryan, is dark matter observed only at the farthest reaches of the universe, or is there dark matter closer? So dark matter is observed at all scales in the universe. It's seen both relatively close by, like when you measure the movements of the stars within the Milky Way. And it's also measured at the farthest scales that we can possibly perceive, which is in the cosmic microwave background radiation, and everywhere in between. So we see the effect of dark matter through the movements of galaxy clusters colliding with one another. So I'm going to run through the various lines of evidence that tell us that dark matter is a thing and sort of give you a sense of the scales for where we're seeing these lines of evidence. So the one that's kind of the closest is the movements of the stars in the Milky Way. And so when you envision all of the stars going around the center of the Milky Way, compare that to the planets that are going around the sun in the solar system. So you've got these planets, for example, Mercury is going the fastest, it's going over 40 kilometers per second, and then Earth is going 30 kilometers per second around the sun, and Neptune is going like 5 kilometers per second around the sun. You've got this drop-off, this very linear drop-off as you get farther and farther away from the sun. And this is what you would expect if you have a bunch of objects that are orbiting around some gravitational center. So the sun with the planets going around it, that's the way you sort of see the change in the velocity of the planets that are orbiting around it. Now, if you do that same measurement of the stars going around in the Milky Way, the stars that are very close to the center of the Milky Way, the ones that are quite close to the supermassive black hole, are moving very quickly. And then the speeds slows down as you get farther away from the center of the Milky Way by a little ways. And then something super weird happens, which is that the speed doesn't change. So even though you're going farther and farther away from the center of the Milky Way, the speed remains exactly the same, or roughly the same, around 250 kilometers per second. And they don't drop off in the way that you expect. And so how is that even possible? The only way that you can have that be possible is that it's not that all of the stars are orbiting around some center of gravity the way it is in the solar system. It's if the stars are embedded in some much larger thing that is just turning, and the stars are turning inside of that thing. And so when you run the math to say, like, how much stuff would it take to get the behavior of the stars as we see them here in the Milky Way and in every other galaxy, you need about 10 times as much mass in the Milky Way as what we can perceive. When you count up all the stars, you get 10 times as much mass. So that is affecting the sun. Now, we don't know if dark matter, if it is like a particle, that there's dark matter particles in you right now today. There's dark matter particles that are moving around in the solar system. There could be dark matter particles. Or maybe there's primordial black holes that are 1,000 times the mass of the sun, and they're tens of light years apart, but they add up on average to making the Milky Way move that way. And so that's very close. And then when you look a little further out, actually the other one is that the speed of rotation of galaxies is too fast. So they should be tearing and shearing themselves apart. But for some reason, the galaxies are able to keep themselves together as if there was more matter gluing them together than what we can perceive. And then when you look farther away, we can see gravitational lensing. So when astronomers map the universe very carefully, they're able to see these distortions of light, where light has made this journey from a distant galaxy to our telescope, but it's been curved and bent and warped. You can actually, like, imagine you're looking through water, like water that's rippling at, say, trees or something. You're lying on the bottom of a pool, you're looking up, there's trees above you, and you're seeing the trees are getting all kind of warped. And so you know that there is water in between you and those trees because you can actually measure. And you could measure the depth of the water if you sort of knew the true shape of those trees and you were able to measure the warps and the changes. And so when astronomers measure just very carefully the structures of the universe, it all looks like it's in a bit of a funhouse mirror, warped and wobbled. And then you can calculate the amount of gravity that would take to distort the path of the light as it's moving from more distant objects to be able to tell you and match what you're seeing. Once again, you need about 10 times as much mass to account for those kinds of changes of the light's path to be able to get to you. And then you've got things like the bullet cluster, where you've got giant galaxy clusters that are colliding together. And what you get is the mass that is the distorting mass seems to pass directly through. As two galaxies are colliding with one another, the stars pass right through each other. That extra distorting mass also passes right through, but the gas and the dust kind of collides in the middle and piles up and heats up. And so we know that whatever this thing is, it seems to hang out with the stars and can be separated from other things. And then we can actually see examples of dark matter where we can see galaxies. When you sort of look for the warps and the wobbles around a galaxy, you don't see it. So there are galaxies that have a lot of stars, but they don't seem to have any dark matter in them. And then you look at other galaxies where you can see this distortion of space, but there are almost no stars inside of it. And so it's a galaxy that's made almost entirely of dark matter. And then at the farthest distances of the universe, we see the cosmic microwave background radiation. And essentially the anisotropies, the changes in temperature that we measure in the cosmic microwave background radiation, could only exist if you had an amount of dark matter in the universe that matches all of the other observations. So there are so many observations for dark matter. Nobody knows what it is, but that's fine, right? Like, this is how it starts. You see a bunch of stuff and you say, that's weird, and then you measure it. So back to your question, dark matter affects us at our galactic level, at the Milky Way's level. So it's whatever it is, it's around us, and also seems to have an influence across the entire universe in every direction as far as we can see. I hope you noticed the Star Trek planet name that appeared above my shoulder. This is a way for you to vote, for you to tell us what you thought was the best question, best answer, combo, whatever you thought was best. So the winner this week was for Dr. Whale Al-Rifai, and asking what would happen to a spaceship that was going at 50% the speed of light and hit a piece of sand. So thank you everybody who voted and chose that as their favorite question answer. Now we will put a different Star Trek planet name above my shoulder for each of the questions, and we'll put them in the show notes, and we'll put a list down below. And so just go ahead and put the name of the question down in the comments down below, and that's a way to vote, and we'll count them up next week, and we will celebrate again. Vincenzo R. How accurate do you feel MOND is to explaining the gravity problem the standard model seems to have? I'm a bit fuzzy on what MOND really says. So MOND is modified Newtonian dynamics. It is another explanation for dark matter. And the gist of MOND is, like all those observations that I mentioned before, that those all assume that gravity works the way we understand it at the local level, kind of like Newtonian, and includes all of the relativistic stuff introduced by Einstein, that we understand how gravity works at various scales in the universe. But what MOND says is that, well, maybe we don't completely understand how gravity works at the largest scales, that when you want to look at scales that are even greater than, say, that which is affecting stars interacting with one another, then you can put in a fairly straightforward additional factor into your gravitational calculations, and suddenly it answers many of the same questions that the particle idea for dark matter does. That if gravity worked a little differently than we understand, then you would see stars moving in galaxies in the way that we see them, that you would see galaxies not tearing themselves apart as they rotated. You would see all of these various observations. But there are some problems. Like, there's a lot of other observations, like, say, that gravitational lensing that I mentioned. It's really hard to say, well, why would one galaxy have a lot of this extra factor for gravity, but this other galaxy has almost none? What is the difference between those two galaxies, right? If we know the total mass of the stars in those galaxies, then we should know how much of a gravitational interaction they should have. Now, there are a lot of people that still think that MOND is the answer, but they're having a harder and harder time these days being able to convince the rest of the astronomy community. And so, this is how science works, that an observation is made, someone says, that's funny. And then people try to explain it, and they come up with theories, and then they make observations and find out whether or not those observations match back against the original theory and provide more evidence one way or the other. And it's been this long process over decades and decades where the evidence is growing that dark matter is some kind of particle, and the evidence is declining that dark matter is just that we don't understand gravity at the largest scales. But MOND has not been completely disproved, and so people come back around almost every week with a new paper that incorporates MOND and comes up with some new ways to account for some of its issues. People address them in the scientific literature, and the conversation goes back and forth. I mean, the other one that you can't rule out is primordial black holes. That there are black holes left over from the beginning of the universe, and they are dark matter. There is no particle. There are just black holes. Does that make you feel better? Damon Gates, thoughts on the lack of impact from the G5 sunspot emissions that hit Earth. So when I'm recording this, we are at the tail end of a series of very powerful solar storms that struck the Earth. I think over the course of a couple of days, we got 8 X-class flares. Maybe it was 6. X-class flares. And the X-class are the most powerful types of flares that the sun gives off. And when an X flare is directed towards the Earth and you get a coronal mass ejection, you get particles coming from the sun interacting with the Earth's magnetic field, you get auroras seen in regions that maybe you wouldn't normally be able to see them. And you also get disruptions in our communication, electrical problems, satellites can go down. So it can be both wonderful because you go out in Florida and see the auroras, but it can also be a little scary because, some of your electronics can have problems. And we know that there are much, much worse versions of solar flares that have hit Earth in the past. The most famous of these is the Carrington event, which hit Earth in the 1860s and was so powerful that people saw auroras around the entire planet. Telegraph poles were lit on fire, and this was a largely non-technological society at that point. And yet, already, just the faint bits of technology that people had were starting to fail. Now, from what I understand, the Carrington event was an X45, which is an extremely powerful solar flare. And the most powerful of the recent grouping that we had was X8.6. And I believe that sort of the process goes up by orders of magnitude. So an X45 is a dramatically more powerful flare than an X8.6. And so you're just not going to get the same kind of damage. We theoretically should be getting these Carrington class events every 1,000 years or so. And scientists have been able to look through tree rings to see evidence of past solar flares, and they've found some really incredibly powerful events that have happened, say, for the past 10,000 years. I think there's 6 events, and the scary thing is that the Carrington event isn't one of them. So the Carrington event wasn't powerful enough to sort of have the evidence of that event be locked into the tree rings. So back to your question, any thought on the lack of impact? We get hit by solar storms all the time. That a 8.6 is nothing. We saw one about 20 years ago. We've seen more powerful ones hit Earth, and we know what the effects are. There can be local damage where, satellites can go down or some electrical grid can fail, like the one that happened in Quebec back in the 90s. But just in general, it's just not a severe enough storm to cause significant problems. So we're approaching solar maximum. We should see many more of these solar storms over the coming months leading up to whenever solar max peaks sometime next year. So this is your chance to see auroras. I wouldn't be worried at all about what effect. And I know, I was arguing with people in my comments saying, this is it. This is the end of the world. No, it's not. It's not. It's fine. just like the asteroids aren't going to be hitting Earth, that, there are channels on YouTube that are trying to freak people out for clicks. I'm not one of them. I'm trying to calm you down for clicks. I'm trying to educate you for clicks. So, yeah. Powerful flares happen all the time. No big deal. Enjoy the auroras. Tom Hodder. If planet 10 exists and is 300 astronomical units away, would it be visible with light telescopes? So I like that you said planet 10. I think, the Pluto as a planet community are going to appreciate the fact that you're calling it planet 10 and not planet 9. Planet 9 is the planet that Mike Brown and Konstantin Batygin are proposing as a maybe Earth-sized world, maybe Neptune-sized world orbiting in the outer solar system, and it's influencing objects in the Kuiper Belt. No one has directly observed it yet, but based on its influence, it's kind of narrowing down the search space for where this thing could be. And the reason it hasn't been found is because it is very dim. So there are plenty of surveys of the entire night sky that have been done to a depth, a sort of dimness of object that would have turned up planet 9 at a specific brightness. It hasn't been found. More detailed searches at even sort of fainter brightnesses have been done in the plane of the ecliptic, in the places where Mike Brown and Konstantin Batygin are proposing this object might be. But a telescope that can make this kind of observations, field of view, is very, very small, and these telescopes are very, very busy. So you can't just say, listen, we need to use the James Webb Space Telescope and we need to search the entire plane of the ecliptic for a mysterious object that is out there. Sorry to anybody else who ever wants to use James Webb ever again. So just to give you a sense, right? The Hubble Space Telescope has been operating for almost 35 years now, and it has probably imaged 0.5% of the night sky. 0.5%. So it's a big sky and it's a very small tube that is trying to look at it. And so there are telescopes here on Earth and telescopes in space that can see to ludicrously faint magnitudes if they know where to look. And this is the problem. Nobody knows where to look exactly. So we're waiting on the next great observatory to come online, and this is Vera Rubin, which comes online in 2025. So next year, Vera Rubin comes online, and this telescope is going to be doing all-sky observations from the southern hemisphere, and that will include the entire plane of the ecliptic, all the places where the planets go. It's going to be able to observe to a very faint magnitude, and because it's going to be observing the entire sky every 3 nights or so, any object like Planet 9 that is slowly moving through the sky, bip, 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 you're going to see its motion every 3 nights. It's going to be this little dot that appears in the next image, the next image, and the next image. It's out there, or it's not, right? And so if Vera Rubin does its observations and it doesn't find anything, then we know that there's some other interesting influence that is causing the motions of these Kuiper Belt objects. And there's a lot of really great ideas, like maybe a rogue planet passed relatively close to the solar system and disturbed all these planets. Maybe there's just this combined influence from all of the stars in our neighborhood of the Milky Way that is causing this change in distribution of the Kuiper Belt objects. So whatever the answer is, it's going to be really interesting. Now, would you be able to see it with a telescope, like a backyard telescope? And I would say no. If you have a very powerful backyard telescope, you can see Pluto, but you would need something that is like a professional science grade telescope, something in the several meters across, to be able to see an object as faint as how faint Planet 9 is going to be. But the most powerful telescopes on Earth, the Very Large Telescope, the Extremely Large Telescope, and of course space-based telescopes like Hubble and James Webb will be able to see it. Like, unless it's incredibly dark and incredibly dim, we'll find it. Vera Rubin will find it, and then everybody else will observe it so much. If you want to support the work we do at Universe Today, consider joining our Patreon club. Now, there's something that I want you to know, which is that you don't have to give us money to be part of Patreon. You can actually join our Patreon for free. You can subscribe, and then you'll get notifications on all of the various things that we post to Patreon. And actually, the vast majority of everything that we do is available for free. Sometimes we release it a day or two early to the patrons, but most of the time, everything is just freely available. So go to patreon.com/universe today to join for free. Now, I want to thank everyone who has already subscribed, and welcome to our recent newcomers. Thanks to Ken Paulus, Arnold J. Ladwig, Marius Daniel, Frederick Wellness, Gail, Andreas Dill, Rev Keith Carter, Edward Welbin, Mind Expansion, Nautilus Studios, and Alaskan Stout. Join the club at patreon.com/universe today. Moonwalker, does a scientist always get exclusive use of James Webb, or can multiple scientists use it simultaneously if what they're observing is pointing in the same general direction? So the time for James Webb is broken up into kind of two, maybe three broad categories. So the first category is dedicated time. And the important thing to remember here is that using the James Webb Telescope is completely free. So anyone on Earth from any country can access James Webb and use it for free without having to pay anything. Now, you're going to have to be an astronomer or a scientist. You're going to have to make a good case for them to grant time on the telescope, but there's a process for scientists to be able to go through this. And so the first bucket is the people who want to make some very specific observation. Like, think about how David Kipping wants to search for exomoons. He's got a very specific planetary system that he wants to point at a very specific time when the planet is going to pass in front of its star. That's the moment to try and observe to see if there are exomoons there. And so the telescope team has granted the time, and in that exact moment, James Webb will turn and point and gather that data. And I don't remember the exact percentage of the time, but let's say a third of James Webb's telescope time is taken up by these direct observations. And so the astronomer who has made the request, made the proposal, then gets a login to a website where they can download all of their data. And they've got a year to have exclusive access to the data that they requested to be able to write their science paper and be able to publish their results. And after that year comes up, all of their data is freely available to the rest of the internet, and anyone who wants can look through that data and see if they can make their own discoveries and observations. The second tranche of observing time is for surveys. And so there's a bunch of surveys, one called JADES, one called SEERS. There's a bunch of stuff that's being done inside the solar system, and extragalactic stuff, planetary systems. And with these, there's a list of targets that are agreed upon in advance. Essentially, James Webb is making its own mini version of the Hubble Deep Field. It's got a specific region of the sky. It's taking a bunch of images, and then those images are being freely accessible to astronomers anywhere. You can go, log in, gather the data, do with it what you will. And the last part of this is called discretionary time. And so there's some time that's left over, and it's a fraction of the leftover time that is available by the committee that's running James Webb if something exciting comes up that needs to be observed right away. So you think about comets or interstellar objects or interesting storms that happen, or if a supernova is seen and requires observations, then James Webb can join in the fun and be able to, be turned and pointing at that object. Now, if it was right in the middle of when David Kipping was trying to make his exomoons observation, then things are going to have to be shuffled around. Time is going to have to be reallocated depending on what happens. But yeah, so in general, either you get exclusive use to the data based on what you've observed, but then you have to share the data with the rest of the astronomers after a year. It's called an embargo. Or you are part of a larger survey, and multiple scientists. Everybody can access the data immediately. Michael Brown, aren't neutrinos a form of dark matter particle? So neutrinos don't explain dark matter, but I really love neutrinos as a way to wrap your mind around what kind of particle dark matter is. And so when astronomers were starting to figure out how fusion worked in the sun, and they did the math, and they said, okay, you've got a bunch of hydrogen atoms and they're getting smushed into helium atoms and they're releasing gamma radiation. If you like carry the one, then there's like a little bit of mass that is missing. And they said, so there should be some kind of particle that is being released that is getting rid of this remainder of the fusion process. And yet we don't see these particles. We don't see like little bullets flying out of the sun, tearing everything apart. What's going on? And so they searched for this object and they built larger and larger detectors, neutrino detectors, and realized over time that these particles just never interacted with anything. And it wasn't until they, I think, had built this giant neutrino observatory next to a nuclear reactor, and they had like a high concentration of neutrinos that were passing through it, that they were able to start actually detecting the occasional interaction with a neutrino and the water. And we now know that a neutrino will gladly pass through a light year of solid lead without interacting at all, and that there are countless neutrinos streaming through your body right now, and yet you don't feel them because they just don't interact. And so the kinds of detectors that are required to find neutrinos are a cubic kilometer of water ice down in Antarctica. That's the Ice Cube facility. And so we already have an example of a particle that is produced by fusion, by supernovae, by various other events that happen in the universe that don't interact in any way. They are not detectable through their interactions with electromagnetic waves. They're not detectable through their gravity, but they're there. And it was finally with the right kinds of experiments that were developed. And it took decades for people to finally go from this theorized particle to this actual particle that was found. And dark matter is kind of exactly the same in that process. Now, its behavior in the universe is very different. It, doesn't interact at all through electromagnetism, despite, it doesn't interact. It's not getting caught in giant neutrino detectors, although people have been trying, but we can definitely see its influence through gravity. And it doesn't interact with itself, which neutrinos don't interact with themselves either. But where things kind of differ is that neutrinos are moving just shy of the speed of light. So they're considered hot. And whatever dark matter is, it has to be moving slow because it sort of holds itself together in these giant blobs around galaxies. And if it was moving it close to the speed of light, then it would be escaping the gravity of the galaxy and it would be flying off into the universe. And so whatever this particle is, it doesn't interact with regular matter. It doesn't interact with itself. Like dark matter doesn't collide with itself, but it's slow moving and must be massive. And so over time, that's what astronomers have been able to work out so far. They've been able to narrow down the search space. But no, neutrinos can't account for dark matter because neutrinos are hot. They move too fast. They don't explain the observations that are made for dark matter. So there's another totally mysterious particle in the universe out there for us to find. Australian. The aurora here in Australia look pink and the northern lights are very green. Is that true? And if so, why? The color of the auroras can be anywhere from pink to purple to green to blue, red, definitely. And so they can sort of run across the entire color spectrum. And it's not whether it's an Australian thing or whether it's a North American thing. It just depends on what you see. So the most amazing auroras that I've ever seen were green, just only green, and just a amazing shimmering curtain of green that went all the way across the entire the sky. And yet other times I've seen red auroras. I saw one that was like a line of red that went just all the way across the sky in this sort of line that just hung there. And we'll show you some pictures. We shared them in Space Bites, but I was in Japan. I wasn't able to see it, but my wife was back here in Canada and she was able to watch the aurora and she got all of the various options. She got some green aurora and she got some sort of pinkish red aurora with bits of yellow in it. Amazing. And these are pictures just off of her iPhone. And yet she was able to see them with this level of clarity. So this last batch of auroras, like if you missed it, like me, this was a really great chance to see auroras, and hopefully we'll get a chance to see more. So no, there's no rhyme or reason to who gets which colors where. Lily Rose, what is the Drake equation? How do you think it goes with the length of the universe? So the Drake equation is an equation that was put together by Frank Drake, and he did this as a sort of talking point for a conference that a bunch of scientists were having, where they were trying to consider and work out how many technological civilizations there are out there in the universe. And so Drake proposed 6 factors. And I forget the exact precise factors, but the gist is the number of stars with planets, habitable planets in the Milky Way, and the percentage of those planets that are within the habitable zone, and the percentage of those that have life that emerged on them, and the percentage of those that have had a technological civilization, and the length of time that those civilizations last, and the amount of information they've communicated out into the universe. And then if you crunch all those numbers together, you can calculate the number of communicating civilizations that are in the Milky Way. And people come up with different numbers. Like, so I found 1,000, I found 1, I found 10 million. And so the problem is that, yeah, we might know what percentage of stars have planets, what percentage of those stars are terrestrial in nature, what percentage of those are in the habitable zone, and we're getting to that part. But it's the, how often does life form? We don't know. It could be anywhere from every single planet life forms to it happens 1 in a quadrillion times, which means that we are the only life in the entire observable universe. And so we just don't know. And when you look at the Drake equation, you can magnify and multiply it. You can think, well, like what percentage of those habitable planets have plate tectonics, which is required for multicellular organisms? What percentage of them have a large moon in a stable orbit to keep its orbital tilt from being unbalanced? And what percentage of them are located within the habitable zone of the galaxy? And so there could be another 1,000 factors that will influence the chance of an intelligent civilization arising and communicating in the universe. But we just don't know those numbers. That one number on how many worlds has life arisen is still a mystery. And until we find any other examples of life out there in the universe, we just don't know. And so unfortunately, as cool as the Drake equation is, and as like tantalizing a thing that it purports to deliver, right? Just run a bunch of numbers through and you will get the number of communicating intelligent civilizations in the Milky Way. Just like that. Now we just have to find them. Well, the problem is that it's garbage in, garbage out. And so if you're just going to guess, then why do you need an equation to guess? Just guess. Come up with a number, whatever number makes you the happiest. So unfortunately, more data needed. Edward Hinton. They say that you wouldn't know that you've passed over the event horizon of a huge black hole, so you could see the event horizon of a black hole and partially put your arm over it. What would happen? So for the small black holes, the stellar mass black holes, then the tidal forces are so extreme that they're going to tear your arm apart. They can tear your whole body apart as you get too close. So you will know that you are approaching the point of no return when you have been stretched into a stream of goo that is now orbiting around the black hole and on its way to go in. But for the supermassive black holes, the ones that have millions or maybe even billions of times the mass of the sun, the gradient of the gravity that you experience is so low that you can fly your spaceship through the event horizon and not even feel it. And yet there is no escape. You have passed the event horizon. You can never come out. And so what would happen if you flew right next to the event horizon and you put your arm into the event horizon? Well, the part of your body that is outside the event horizon could theoretically, if you're able to move your spaceship at close to the speed of light, could escape. But the part of your arm that you put into the event horizon is going into the black hole. It is a one-way trip. You do not come back out. So it doesn't matter whatever you try to come up with. Like, take a camera, put it on a long pole, stick it down into the event horizon, and then pull it back out. And you're like, there's no camera there anymore. It's just gone because nothing gets out. All roads lead to the singularity, and there's no There's no way around it. So just inside the event horizon, going into the black hole. Outside the event horizon, there's a chance you could escape. All right, those are all the questions that we got this week. Thank you, everyone who joined me for the live show and asked me questions live here on the channel, as well as everybody who posted their questions into the YouTube comments. So I really appreciate that. Now, we record this show live every Monday at 5 p.m. Pacific time. So if you want to have a much longer 2-hour experience of the question show, come join us. There'll be a notification here on the channel. Subscribe to the channel, click on the notifications bell, and you'll be informed when we go live next Monday. Now, I'm going to talk about my recent trip to Japan, but first I'd like to thank our patrons. Thanks to Abe Kingston, Andrew M. Gross, David Giltonan, Dennis Alberti, Dustin Cable, Jeremy Matter, Jim Burke, Jordan Young, Josh Schultz, Modso, Paul Rohrbach, Stephen Krasaki, Stephen Fowler-Munley, and Vlad Shiplin, who support us at the Master of the Universe level, and all our other patrons. All your support means the universe to us. So you're probably wondering what happened to the question show for the last 2 weeks, and that's because I was in Japan with my son. Now, this trip, originally, we were going to take 4 years ago in March 2020, but then the pandemic hit, and so we had to cancel the trip. And so we waited, and now we finally were able to do it. And I am so glad we got a chance to go back. Now, we didn't do any spacey, sciencey stuff. It was more going and seeing temples and shrines and eating amazing ramen and riding on bullet trains and just having a great time. But I'm so glad that I went, and sort of thanks to everybody who we got a chance to hang out with in Japan. The hospitality of the country is incredible, and just like the level of culture and organization and the food. So if you're wondering like, oh, I kind of am intrigued. I like anime. I'd like to maybe go to Japan. Do it. It's such an easy country to travel in. There's English on all the signs. Most machines that you can access, you can switch to other languages. Everybody is very warm and generous, and the prices are reasonable now, which I know is sort of hard for the Japanese economy, but for a person who is coming from another country, your dollar goes pretty far. So I'm going to go back pretty soon, I think. Take my other kid to Japan for a different adventure. So anyway, we're back with the show, and I hope to go back again and do more traveling. All right, we'll see you next week.